Hello, ladies and gentlemen. Today we're going to be talking about what's called the remainder theorem and then a subdivision of that called the factor theorem, and how we're going to use basically what we've been talking about the last couple of weeks, synthetic division and long division, to fully factor these larger polynomials that we're looking for, okay? So the remainder theorem is a pretty powerful theorem that if you have a polynomial that you divide by something of the form x minus k. So the things that we've been doing with synthetic division, right? Dividing by these binomials that are x plus a number, x minus a number. The remainder that you're going to get if you do that division is always going to be equal to, so the remainder will be equal to f of k. Basically, if I plug in the value that I'm dividing by into the function, what I get out, the output I get, will be what the remainder will equal, okay? So I plug it in, whatever I get out, that will be the remainder. Now, that's cool, all right, nice to know. Why do we care? Why is it helpful for us? Why do I need to know what the remainder is? Because of the factor theorem. If a polynomial is a factor, then its remainder will equal 0. Meaning that if I plug in the k value into my function, that will equal 0. Now, kind of makes sense. If it's a factor and I plug in the k value, I get out 0. Yeah, of course, that's what kind of makes it a factor, right? Because that's when y equals 0. But that's good to know because it's a way for us to check if we have certain binomials are actually factors of a larger polynomial. So for example, if I had x minus 2 and x plus 3, and I told you, hey, these are factors of this polynomial over here, you can plug in 2 and negative 3 into this function to see if they are actually factors. So I could plug in 2 into the function, and I could plug in negative 3, and we could check to see if we actually get 0 out to tell us that they are in fact factors. So if you have a calculator handy, I have one right here. Okay, you go ahead and you plug these in. So I plug in 2, and I in fact got 0 to come out. Same thing with negative 3. I go ahead and plug in negative 3 into my function, and once again, I got 0 as my output, meaning that these are in fact factors of this polynomial. Since we know that, we know we can divide, and we will get we can divide by them and we will get no remainder, and we'll be able to get kind of like a clean answer that comes out. So we are going to use that fact to fully factor this polynomial. Basically use this theorem up here and be able to check that these are factors to fully factor this. Okay, Mr. Guy, cool. How do we do that? By doing synthetic division, what we've been talking about the last couple of days. So what I'm going to do is I'm going to do synthetic division first off with the x minus 2. So I'm going to draw my little bar, put my 2 over here. I have 2, 7, negative 4, negative 27, and negative 18. And again, I kind of know that my remainder should be 0, right? So if I do this and I don't get a remainder of 0, something obviously went wrong, okay? Bring down the 2. 2 times 2 is 4. Add those together, get 11. 2 times 2 times 11 is 22. Add those together, I get 18. 2 times 18 is 36. Add those together, I get 9. 2 times 9 is 18. And look at that, I got a remainder of 0. Okay, so dividing by this, I get 9 and 18x and 11x squared and a 2x cubed. All right? Meaning that my original polynomial can be written as this times the x minus 2 that I divided out. Okay? So basically, it's like I factored out an x minus 2 from this polynomial here by doing the synthetic division. Cool. But I also want to take out this x plus 3. So guess what I'm going to do? I'm going to do a synthetic division problem again. But this time, I'm going to be using this polynomial right here, because I'm going to take it out of this, and we're going to factor down even more. So I'm going to say, all right, I got 2, 11, 18, and 9. So we bring down the 2. 2 times negative 3 is negative 6. Add those together, I get 5. Multiply, I get negative 15. I get 3. Negative 9. 0. Once again, I got a remainder of 0, exactly what I wanted. And the answer to this was 3, 5x, and 2x squared. Okay, so this polynomial that's left over. So again, I can now factor this even more. I still have the x minus 2. I'm also now taking out an x plus 3. And what's left over is 2x squared plus 5x plus 3. I'm almost done fully factoring my polynomial, but I need to now factor this portion over here, which you'll notice is a quadratic. That's kind of going to be our goal as we go through and we start talking more and more about fully factoring polynomials. If we can pull off factors until we're left with a quadratic, we know how to factor a quadratic already. We've talked about a lot of different ways to do that, and so we can go ahead and we can factor from there, okay? If I want to factor this by grouping, I can go and see, all right, I get 6. So I want something that adds the 5 and multiplies the 6. That's going to be, I'll kind of do this over to the side. So that's going to be 2 and 3. So we'll split this into 2x squared plus 2x plus 3x plus 3. We then are going to go ahead and we're going to take out GCFs. So over here, I'm going to be taking out a, we're going to take out a 2x and be left with an x plus 1. And then over here, I'm going to take out a 3 and be left with an x plus 1. I notice that I have x plus 1 in both spots, so I'm going to factor that out and get x plus 1 times 2x plus 3. And so our polynomial fully factored is x minus 2 multiplied by x plus 3 multiplied by x plus 1 multiplied by 2x plus 3. Those are all the factors of this polynomial. We just fully factored to the 4th power polynomial. Okay, that's pretty good. All right, that's a big polynomial, and we just fully factored it here. And now I could use the zero product property to find all my roots. Right, set these all equal to 0, solve them, and you could find all your roots from there. Okay, but that's how we're going to fully factor these polynomials. And again, it comes down to kind of the main thing from today, this remainder theorem, specifically the factor theorem. Right, if I plug in the k value, whatever comes out will be my remainder. If I plug it in, I get out a 0. That means that that original binomial is a factor. Okay, it's a factor because when we plug it in, we got out 0. Okay, that's the remainder theorem and the factor theorem. Thank you all for watching.